Alright guys, so now we are going to study the section 2.1, graphs of basic functions and symmetry. In the example number 1, it's all about function, continuous function or not, and let's take a look at the different example. In the example 1a, what do we have? Basically you need to understand that when I graph my function f of x equal x cubed, I realize that without picking up my pencil, I'm able to graph my function. And so the interval is going to be minus infinity plus infinity. If I had to graph the function on the Cartesian system coordinate with a different scale, I would probably going to have something like this. This way you can see much better that we are going toward plus infinity on the x-axis, and we are going toward minus infinity on the x-axis right there. When I look at the second example, this graph is a continuous everywhere. It's continuous everywhere except when x equal 1. I got an open circle, you see, a solid dot right there, and it's at x equal 1 right there, x equal 1. So this is why we are going to have the minus infinity 1 and then 1 infinity with a union in between. Why do I have a parenthesis nearby the 1? Because 1 can be a solution as we having a jump. Okay, let's try to look at, let me erase that, and let's try to look at the last example. This graph has an open circle and a closed circle at x equal 2. Open circle at x equal 2 and solid dot or closed circle at x equal 2. For that reason, it's not a continuous. Just right here, x equal 2, it's not continuous. However, it is continuous between minus 4 and 2, and it's also continuous between 2 and 4. You have a solid dot in 4, you have a solid dot in minus 4. This is the reason why we are going to have minus 4 bracket because of the solid dot, and nearby the 2, open circle, so parenthesis, union, 2, 4 for the same reason on the other interval. However, so we will use, I will repeat, we will use the bracket when you have a solid dot. So right here we are supposed to use a bracket. When you have an open circle, it's supposed to be parenthesis. I'll let you looking at the example number 2. You will see it's very simple, very easy. It's about the same order than that we did in the example number 1. Let's take a look at the idea of symmetry. And to define if an axis is symmetry or not, you need to remember perfectly well these three tests. If it is if x is the axis of symmetry, you just need to replace y by minus y, and if you have the same equation at the beginning and at the end, it is the axis of symmetry. You do the same idea, it's the same idea with the y-axis. You replace this time x by minus x, and if you have the same thing, well, that means y is axis of symmetry, and at least at the last one, if you want to test if the origin is the symmetry, you replace y by minus y and x by minus x, and then you simplify. If you have the same thing than at the beginning, that means the origin is a symmetry. So let's take a look at the first one, and let's try to decide if x is an axis of symmetry. So if x is an axis of symmetry, I'm supposed to substitute y by minus y. So that implies that x squared plus y equal 9 is going to become x squared plus minus y equal 9. That gives me x squared minus y equal 9, and I can see that these two equations, the equation number 1 and the equation number 2, are different, so X is not axis of symmetry. Okay? X is not the axis of symmetry. Now, let's focus on the B. Well, B, as you can see, it's already done. So if you take a look at it, you substitute y by minus y. You will pay attention that we use the parentheses. Okay? Use of parentheses for minus y. And when you are squaring minus y squared, you end up to have exactly the same equation. The equation right here is exactly the same than the equation right there. So x is the axis of symmetry. When you're doing the same with a y axis of symmetry or not, you end up to have exactly the same thing. And so you end up to say that y is also the axis of symmetry. Can we say that the origin is a symmetry? Well, when we substitute x by minus x and y by minus y right here, we end up to have the same original equation. So the origin is, we can say that we're having an origin symmetry. Okay, so that is super duper important for you to remember. I should have underlined these three definitions. Please underline them and pay attention to them because you will use them a lot. And right there you have a perfect example on how do we define if a function is increasing or decreasing. Well, we take two values of x, okay, and we are looking at what is the highest value. Well, in this case x2 is greater than x1. If you have x2 greater than x1 and f of x2 greater than f of x1, well, that means it's increasing. So I could write right there x2 greater than x1, and then we're having f of x2 greater than f of x1. So that means it's increasing. Now, if I have x2 greater than x1, but f of x2 this time is less than f of x1, that means it's decreasing. Decreasing. And if you have the same thing, x1 less than x2 and f of x1 equal f of x2, that means it is a constant. Okay, it is a constant. All right. So you have to remember that we are reading the domain on the x-axis, so on the horizontal, and the range is read on the vertical. All right. So when I look at the linear function f of x equal x, and I want to look at the domain, I'm going to look at the domain on the horizontal right there. That's the domain. And the domain is going to be minus infinity plus infinity. Okay, always parentheses next to plus infinity. Regarding the range is vertical, and I can see also that the range is going to be minus infinity plus infinity. Same thing. Okay? If I look at f of x equal x squared, I'm going to have exactly the same thing. I'm going to have the domain read on the horizontal. Let me do that. I don't like this. And if the domain is read on the horizontal, I can tell that it's going to be minus infinity plus infinity. Okay? But regarding the range, I can see that the range, even though it's read right here, it starts from here, and it starts from 0 to plus infinity. So at the end of the day, the range is going to be 0 plus infinity, and then it's going to be so 0 plus infinity, and it's going to be a bracket nearby the 0 because 0 is a solution of your function. Okay? All right. Now that's done. We can do exactly the same thing for the cubic function. I'll let you do that home. Please look at your book. Okay, you should have everything in your book. So you can do that home. You can do also this one that home. Actually, I would like you to check this one because they are done already. So please check these three to make sure that there is no mistake. And these are what you need to remember to define if it is a x-axis of symmetry or not, and how to define the axis of symmetry. So let's jump on the example number 3. I'm going to do one of them, and I'm going to do the number 1. If I want to define that x is the axis of symmetry, so if I want to define that x is axis of symmetry, well, I'm going to substitute x by minus x. So if I substitute x by minus x, what do I have? Well, I'm going to have y equal minus x cubed plus 4 times minus x. That gives me a y equal to minus x cubed minus 4x. Obviously, we don't have x as an axis of symmetry, so x is not the axis of symmetry. Do we have y, the axis of symmetry? In that case, I need to substitute y by minus y. So I'm going to have minus y equal x cubed plus 4x. At the end of the day, that gives me a y equal minus x cubed plus 4x. Obviously, y is not the axis of symmetry. Do we have all origin symmetry? And for that, I'm going to substitute y by minus y and x by minus x. Okay, and then I end up to have minus y equal minus x cubed minus 4x, which is y equal x cubed plus 4x. And that implies that we're having origin symmetry. Origin symmetry. I'll let you finish the B and the C to define what is the symmetry for each of these equations. Alright, now even function and odd function. Please pay attention to what is an even function and what is an odd function. An even function, all exponents are even number, have y axis of symmetry. Odd function, all exponents are odd numbers. Okay, so all exponents are odd numbers, have origin symmetry. So odd function, origin symmetry. When even function, all exponents are even numbers, have y axis of symmetry. In that case, I have a 2, I have a 4. This is an even function. And that implies y axis of symmetry. Now, if I look at this one, I got a 3 and a 1, which is odd number, so I have an odd function, and that is a odd function. That means it is x as an axis of symmetry. For this one, I got y equals 3x squared plus 5. What do we do? Well, it's neither odd and neither an even function.